Okay, so let's look at applying this phase change information to our problem. So remember the calculations we did on specific heat capacity, because we're going to be applying the phase change to a system where part of that system is going to be changing temperature as well. So let's look at the problem here. We want to make a glass of iced tea. We take some 250 milliliter tea at 18.2 degrees, so that'd be pretty warm for tea, and we pour it into a glass that has 5 ice cubes. So it says down here at the bottom, assume the ice is at 0 degrees C. Okay, so if the ice is 0 and the tea is 18.2, the tea is hot, the ice is relatively cool. That means heat is going to flow from the tea into the ice. So we should think about, right, the amount of tea that, or the amount of heat that flows out of the tea is going to equal the amount of heat that goes into the ice. That's going to be important for solving this problem. Now, 5 ice cubes, each is 15 grams. That would be a total of 75 grams of ice. We want to calculate what quantity of ice will melt, how much of the ice will float to the surface in the beverage. So the problem is telling us some of the ice is going to be left over. And what that means is that the tea and the ice are going to reach a point where they're at the same temperature. And since the ice is at 0 degrees C, that would be at 0 degrees C. So what we want to figure out is how much heat is going to come out of the tea to get it to 0 degrees C. So heat that comes out of tea as it cools to 0 degrees C. Now we know that heat for a system where it is changing temperature is equal to specific heat capacity times the mass times temperature change. Okay, we've seen that equation a few times already. We're told at the bottom to use 4.184 for the specific heat capacity of the tea, right? And it's almost all water. So that's reasonably good. For the mass, we have the volume. We're told to use 1 gram per milliliter as an approximation of the density of the tea. That would mean 250 milliliters would weigh 250 grams. Right? That's 2 sig figs. We'll have to keep track of that because that's going to limit us overall in the problem. And then temperature change is the last piece we need here. Now the tea was at 18.2. Based on the description in the problem, we know it's going to go down to 0. So I'm going to use 18.2 degrees C for the temperature change. Right? Here's a place where you could use negative 18.2, and that would make your Q have a negative value. But again, I'm using the descriptor out. Heat's going out instead of calling it a negative number. So if I multiply all those together, that'll give me the amount of heat that is going to leave the tea and move into the ice. So 4.184 times 250 times 18.2, that is 19,037.2 joules. Now again, our 250 would limit us to 2 sig figs, but since we're partway through a problem, we don't want to round, particularly if we're rounding down to 1 or 2 sig figs. It could really change the final answer we'd get for the calculation. Now, this is the heat that was removed from the tea. That's the heat that goes into the ice. So that is going to be equal to the heat that goes into the ice. Now, since the ice is undergoing a phase change, right, it's at its freezing point, we don't need a temperature change because the heat going in is not going to cause a temperature rise. It's going to cause the ice to melt. So in this case, we can take that quantity of heat, 19,037.2 joules, and we can convert that directly to what mass of ice that heat could melt by using the heat of fusion. Right? So a little bit higher on the page, the heat of fusion is 333 joules per gram. I want to put the joule part of that on the bottom because I'm canceling with joules from my initial heat. So I'm going to divide by 333 joules here. 1 gram of ice would go on top. Right? The joules cancel out and we get grams here. So the important thing to recognize here, if there's no temperature change, you're not using the specific heat capacity formula. That is the one place students will tend to go wrong here, is they'll try to shove it into this formula and there's no temperature change. If it's just phases changing, it's staying at the same temperature. It's just mass and heat, or sometimes the heat of fusion or heat of vaporization could be in terms of moles as well. So in this case, 19,037.2, and I'm dividing by 333 joules, gives me 57.17 grams. Okay. Now, that was 2 sig figs, so keep that in mind as well. Could round to 57 there, but we aren't quite done with the problem, so it's probably best not to round just yet, because that is the mass of ice that melts. That is not the final answer we were asked for. The final answer we were asked for is what quantity, what quantity of ice will melt. That's part of what we were asked for. And how much ice will float to the surface. That's the other thing we were asked for. So we want to figure out how much ice is left. So 5 cubes at 15 grams each. We started with 75 grams of ice. We're subtracting 57.17 grams that melt, and that will tell us how much ice is left over. Now the 75 is also only 2 significant figures, but even more important for subtracting, the last one is in the ones place, so our answer here should be in the ones place as well. So there'd be 18 grams of ice left over after we got to 0 degrees C. Okay. Now that's a reasonable question. But I think this question would be even more likely to not give you quite as much information. So you don't need to be told that not all the ice is going to melt. You could just be asked what's going to happen here. And you've got all the information. You can figure out how much heat it would take being lost to bring the T down to 0. You could also figure out how much heat the ice is capable of absorbing. If it turns out all the ice is going to melt, that would bring the T down to a certain temperature, and you could figure that out. You could figure out which one is a larger quantity, almost like a limiting reactant problem. Right? This is how much I would need to cool my T all the way off. This is how much I would need to melt my ice. Which one is smaller, which one is larger will help you identify whether the T is going to make it to 0 or whether the ice is all going to be melted. Now, if the ice is all melted, this would be a little more complicated problem, because now you'd have a quantity of T at a certain temperature and a quantity of liquid water that has just melted from the ice that's at 0 degrees C. But you could figure out then what should the overall temperature of those two liquids when they mix together be. Okay. All right, let's look at one more example here, and perhaps I should have done this one first, because this one's a little more straightforward in terms of what's happening, because instead of the heat coming out of the T going into the ice, this one is all going in the same direction. We want to calculate the quantity of energy in joules required to raise the temperature of 454 grams of tin from room temperature, 25 degrees C, to the melting point, 231.9 degrees C, and then melt the tin at that temperature. So basically we have two different things happening here. We are starting at 25 degrees C, and we're going to heat to 231.9 degrees C, and that would be tin. So we've got solid tin at 25, and that'll be still solid tin at 231.9. But then we need to add a second quantity of heat that isn't changing the temperature. It is changing the phase of the tin, changing the tin to a liquid. So there's two quantities of heat here. I'm going to call them Q1 and Q2, and different things are happening, so there'd be different ways of calculating those quantities. So for Q1, the temperature is changing, and that means we need specific heat capacity. So Q1 would be equal to the specific heat capacity of tin times its mass times how much the temperature is changing. Now, some of that information is given in the problem. The specific heat capacity of tin is 0.227 joules per gram degrees C. Right? Metals are really good at absorbing heat, so you may have noticed the specific heat values are pretty low for metals compared to things like water, where it's above 4. So water, it's not easy to change the temperature of water. It's pretty easy to change the temperature of metals. You may have noticed that cooking too. The pan heats up a lot faster than the water you're using to make your macaroni or whatever it is. The mass of the sample is 454 grams. It was given in the problem. And then the temperature change, if we go from 25 up to 231, that would be 231.9 minus 25 is 206.9 degrees C. Right? And that'll give us a quantity of heat. But remember, that's just part of the heat that we're going to need here to do this entire transformation. So multiply all this out. and we get 21,322.7 joules of heat. Although, let's keep in mind 3 significant figures, so that 3 would be the last significant place in that quantity of heat. Now, the other quantity of heat is going to be associated with the phase change here, taking the solid tin and making it into a liquid. That's going to come from the enthalpy of fusion. And I snuck in a word here that we'll learn about in a minute. Heat and enthalpy are used interchangeably. Right? Ideally, I wouldn't have used enthalpy yet until we described what it is, but they're the same here in this case. This is the amount of energy it takes to melt the tin. So if I have 454 grams of tin, and it takes 855 joules to melt each gram, grams is going to cancel out. This will give me the amount of heat I need to do the melting. 454 times 855. That is 388,170 joules. Right? That's also 3 sig figs, so that one's actually only going to be significant to there. So that's the last place we can have a significant figure in our answer. The total here will be adding these together. So Q1 plus Q2, and that would be 21322.7. That would be something went wrong there. Try that again. 388,170 plus 21322.7. So that's 409,492.7 joules. But again, 3 sig figs, so 409,000 joules. And that's a little better written as 409 kilojoules, although I'm running out of space on the page there. But numbers that high, it's probably good to change it to kilojoules. Okay, so watch out for that. Look for temperature changes and phase changes in your problems, and we'll pick up on the next page in the next video.